Hi, I'm Daniel Chan from UNSW Sydney. Welcome to another adventure in pure mathematics. The notion of an exact sequence is the fundamental language in homological algebra that we use to record a lot of information about modules. And for the case of exact functors, these are very important because they allow us to work very well with modules and in a very, very easy way. Unfortunately, a lot of functors that appear in algebra are not exact. And what I want to do in this video here is introduce the long exact sequence in homology, which is a way to overcome this deficit and to study functors which are not quite exact. And it's a rather curious sort of situation. What we'll do is, rather than looking at exact sequences of modules, we're going to look at exact sequences of complexes of modules. So that's what we're going to start. We'll fix some sort of a ring and we'll look at chain complexes of R modules. And here we're going to consider a short exact sequence of such chain complexes. Okay, 0 to C double prime to C prime to 0. Okay, so the way you should imagine it, here's our C double prime, here's our complex here. Okay, and then this maps to C. This is our complex here, so there's going to be maps here. All the squares here commute, and all of these double prime modules inject into these modules C here. And these in turn surject onto the C prime complex, so you have surjections of all these modules. Of course, the kernel of these maps on the right-hand side here is equal to the image of the maps on the left-hand side here. Okay, so for each of these short exact sequences, okay, so you get some map, and certainly you can apply functors to them. And one functor that we can apply is, to this short exact sequence, is we can apply the homology functor, okay, at each and every stage, okay. So for example, we can apply the I plus first homology to this to get a map from hi plus 1c double prime to hi plus 1c, and also then from there to hi plus 1c prime, and similarly for hi, and hi minus 1. But what's really, really curious is that these look like separate sequences, but now we can actually connect them with what's called the connecting homomorphism. And the connecting homomorphism works like that. It's going to be a map which goes from, for example, the end of this one here back to the beginning of this one here. And the same happens over here. And this is all the time. That's the connecting homomorphism. So that's what I wanted to find. Let's just do the one from here to here. So that's hi of C prime to hi minus 1 of C double prime. Okay, so let's see how that works. I won't go through the whole details, but it's very curious to see how it works. Okay, so we're going to start with something inside here. So that's a coset of a cycle. So we start with some Z prime that's in here, and it's a cycle in the sense that it will map to 0 here. Okay, so it maps to 0 here. And it's a coset of something like that. And we want to end up with a cycle over here and its coset. Okay, so how do we get from here all the way to over here? Okay, so this is hi minus 1 of C double prime over here. Well, the first thing is that this is a surjective map. So we can pull it back arbitrarily, but there's some sort of choice involved. And I won't go through it, but one of the things that you need to check is that this will be independent of the choice. Okay, so then once you're here, well, I guess we have to get down here. So I guess we can push it down. So we push that down to something inside here. I'll call that C bar. Okay, of course, we want to end up inside here. Now remember, this is essentially, via this map here, just a submodule of that. So maybe this already sits inside here, and to check, well, since the image of this is the kernel of that, we just have to check that this goes to 0. So where does this go to? Well, let's follow this around. Going around this way is the same as going around this way. This goes to 0, so this is 0. So that means that this actually comes from here. So you have some C bar double prime that actually maps to this. Okay. And this element here is the one that defines this element, the image of the Z prime, okay, the coset with Z prime, under this connecting homomorphism. Okay, this is the element there. Okay, so I guess to check that it really is inside there, what you need to do is you need to check that it goes to 0. Okay, so how do you know it goes to 0? Where does it end up? Okay, well, the only thing we know about it is it comes from here. And where does this go to? Well, when you apply this twice, of course, this is a complex, so this goes to 0. And this is something which maps to 0, but this is an injection, so this has to be 0. So this is actually a cycle. And the only other thing now to check this is well defined is that it doesn't matter what element of this boundary element is, and also what element you pick for this C. So let's just do one of them, okay? If we change this, how can we change this? I guess if we change this, we have to change something that's in the kernel of this map, which is the image of that one. And well, if it's changed by the image of that one, how does it change? Well, you just go down here, it will change by a boundary. So you're only changing by a boundary. And similarly, if you change by a boundary of something here, you can check that it's only going to change by something that's at worst a boundary here. And that's how you define the connecting homomorphism. Okay. So what's really, really interesting now is that not only do you have this sequence here, but this is actually an exact sequence. Okay. So remember, one of the things that you should realize is that the exact sequence is a way of giving information about whatever modules happen to be in this complex, okay? So it's information about what's in here, okay? And it turns out to be a very useful way of recording information. The information that you know, unfortunately, it's not complete information usually, but it is some information, okay? And depending on how well you know the maps inside here, that will tell you how well that information is given, okay? So this wonderful theorem, it's called the long exact sequence in homology, is actually not difficult to prove. It involves ideas and techniques similar to how I've proved this, or rather constructed this connecting homomorphism here. Okay, this is known as diagram chasing. And unfortunately, to do it, you actually have to take cases. Okay, so there are 3 types of cases that you have to consider: exactness at the double prime position, at the usual position, and also in the prime position. So maybe just to show you that it's actually not difficult, I'll show you what happens when you want to check exactness, for example, here at the HIC prime dot. Okay, so let's check exactness here. And what I've done is I've just basically recorded the same information that I have, just this portion of the diagram. I've just repeated here, and I've also repeated how the map works. Okay, so basically connecting homomorphism is you start with a cycle here. Okay, you arbitrarily pull it back to here. It doesn't matter which one. We check why that's true. You push it down in the complex by the boundary in the complex. This happens to go to 0 here, since this is a cycle, so you can pull it back over here, and that's going to give you a cycle that defines a homology class down here. Okay, so that was the connecting homomorphism. Okay, so the first thing you need to do to check exactness here is it's a complex. So when you go from here to here, back over to here, you get 0. Okay, so let's start here. So we're going to start with an element here, which is a cycle. Okay, and then what is HI of that cycle? Okay, or rather the homology class, well, you map it down to here. So in that case, you can start with C as a cycle and it maps to the Z prime. And then you take the Z prime and you have to pull it back. Well, when you pull it back, you might as well have picked the original cycle that you had here, which is C. And then when you go down here, well, it's a cycle, so it goes to 0 here. So it goes to 0. So it's certainly true that if you start with a cycle here and you go around here, you get 0. So it is a complex. So the more interesting thing is that suppose you have something that's in the kernel here. Suppose the Z prime here lands inside the kernel here. Okay. How can you show it comes from a cycle in here? Something in the kernel? Okay, so let's do that. So let's suppose you start with the Z prime, and it's going to go towards 0. And what does it mean to be 0 inside here? It means it's a boundary. So it's a boundary, so it's in the image of the boundary map in the complex. So that means I can lift it up to some C double prime here. Okay? So of course, there's some choice in picking what this could be. What do we want to show? Okay, we're saying that this Z prime, which corresponds to an element here, is going to 0 in the homology over here, which means it's a boundary, okay? And to do that, we picked this choice of this element C inside here, which might not be a cycle, so it might not go to 0 here, right? And we want to show that we can actually have picked it to be a cycle. So how do I get a cycle? Well, remember, how can I change this C? Well, I can modify it by something in the kernel of this, which means something in the image of that. So I'm going to modify it by this C double prime. Okay, so the image of the C double prime is going to be the C double. And I'm going to look at, instead of this C mapping to that, remember this is an image of that, so it goes to 0 here. I can instead replace it with C minus C tilde. That also maps to Z prime. And I claim that this here, this C minus C tilde actually goes to 0. And why is that? Well, where does C go to? The C goes to the C bar. And where does the C tilde go to? Okay, the C tilde, okay, came from C double prime, which goes to this C bar double prime, which goes to this C bar. So when you look at the difference of these two, where it goes to is C bar minus C bar, which is 0. So this is a cycle. And that shows exactness at HI C prime dot. And using a very, very similar sort of diagram chasing argument, you can show exactness here and here, and you get this lovely long exactness. It looks very strange and it seems difficult to draw information from that, but it turns out that this is one of the key tools in homological algebra. I hope you enjoyed this adventure in pure mathematics.